about 3D NAND will be covered in professor's lecture later. So today I will just introduce some brief NAND Flash overview and 3D NAND structure and architecture and the process flow and the state-of-the-art 3D NAND techniques. Okay, so this is the overview. So NAND Flash has the highest density among the every silicon-based memory devices, such as compared to DRAM or SRAM, compared to any other memory devices. NAND Flash has the highest density. And the other characteristic is that it is non-volatile. You know what is non-volatile? That means the stored data is preserved when the power is off. It is always preserved. So because of this, NAND Flash is used for mass data storage, such as okay. So in this left figure, around 10 or 20 years ago, you could see this film or floppy disk and CD, feature phone or HDD. But all of these storage devices are replaced by NAND Flash. So now micro SD and USB and some storage device in smartphone is also NAND Flash. And you can also see HDD nowadays, but many portion of the HDD is now replaced to SSD. And these devices are familiar with you, the personal customers, but after year of 2010, some companies, that YouTube, Facebook, or Amazon and Google, that companies use large data centers. They are also a big customer for the NAND Flash company. Okay, so let's look into the NAND configuration. So this is the data center, and there is many SSDs are here. And if we just look into just one SSD, this is one SSD. So there are many NAND Flash packages. And if we just look into one package, there are sometimes 4 or 8 NAND chips are packed in just one package. So this is one package, and this is one NAND chip. And this area is called the peripheral circuit, and this area is the memory cell array. So if you just look into this array, the memory cells have NAND type configuration. So we call it NAND Flash. I will briefly introduce the array structure of NAND. If you look at the left side figure, this is NOR Flash, a little bit different from NAND Flash. So it looks like normal memory array. That means it is one memory cell, and word line and bin line is all connected to all of memory cells. DRAM or SRAM or NOR Flash, all the other memories have this connection. Word line and bin line is all connected. But in NAND array, if you just look this cell, the drain side of the memory cell is connected to the source side of the neighbor cell, right? So the advantage of that is we don't need this metal contact area. So it is serially connected, so we don't need this additional metal contact area. So we can maximize the cell density. So because of this, the memory cell density can be really high compared to other memory devices. Okay, so before I explain about the NAND Flash fabrication technology, I think it is better to know why we developed NAND Flash Fabrication technology. What is the main purpose of company? What is the main purpose? Why do they work?
To make money.
Yeah, to make money, to make profit as much as possible, right? So, what engineers can do is cost decrease. You know that profit is income minus cost. So what we can do is just cost decrease. So cost decrease compared to the previous version, that means previous product, we have to decrease the cost. So how to do that? There's several factors that is related to the cost. The first is the number of chips per wafer. For example, if we can make chip size around 30% smaller than the previous one, we can make then the number of chips can be increased more than 30%. That means the cost could be decreased as 30%, right? So this number of chips per wafer is the most important factor, and this is why we developed the NAND Flash Fabrication technology. But what I mentioned, that the 30% cost decrease is true when the other factors are maintained the same. That means there is also the other factor, the number of wafer per time. That is similar term to the number of process steps. So most of the case, the new technology has the complicated process compared to the previous one. So every time the number of process steps increase and the time also increase. So for example, if we can make 30% smaller chip, but if it takes 30% more time, and how is that? How is it? Is it good? Is it new technology? It could be called new technology, but it cannot decrease the cost, right? So we have to also concern about this factor. And the third one is the investment cost. It includes equipment cost, and labor cost, and material cost. And among these three factors, what is the most dominant one, do you think?
The equipment.
Equipment.
Right. Was it too easy?
Yeah.
Yeah, because you could know that. Okay, let's estimate the total cost of one wafer. So you can estimate in news, just in news and papers. You can find it in Google. So okay, there are some sentences that blah blah. NAND flash costs about 8 cents per gigabyte. And second one is 512 gigabit NAND flash. The chip size is 128 millimeter square. And the estimated NAND flash capacity of Samsung is 4,000 K. That is around 4 million. Okay, so let's guess. How much is one chip? One NAND chip. 512 gigabit NAND chip. How much does it cost? So you can find it 8 cents per gigabyte, right? And the capacity of one chip is 512 gigabit. So 512 gigabit is in gigabyte. It is 64 gigabyte, right? So 64 gigabyte times 8 cents is around $5, right? 512 cents. So that is around $5. And how much? And how many chips are there in just in one wafer? we can also know that from this chip size. Chip size is more than 100 millimeter square, and one wafer, how large is it?
12-inch.
Yeah, 12 inch. So the diameter is 12 inch, that is 300 millimeter. So the area, you can calculate it, and then divide by this chip size. So the answer would be around 500 chips in one wafer. So one chip is $5, and there's 500 chips in one wafer. So in total wafer, it costs around $2,500, and I think it is more than that, 3,000 or 4,000, like that. So it is very expensive. It is not the selling price. It is the just cost. So you can compare this cost with your salary. So you can know that our labor cost is not a big deal. Okay. Now we will just focus on the number of chips per wafer. Yeah, the dominant factor. So how to increase the number of chips per wafer? So in the era of 2D NAND, technology node was scaled down. So you can see that many years ago it was like 27 nanometer, but finally it decreased down to 14 or 15 or 16 nanometer. But it could not be done below this 14 nanometer because of the scaling challenge that is called cell-to-cell interference. Maybe you can, maybe professor will explain about this later. But anyway, so all companies gave up to develop the 2D NAND at this point. So all companies, and then all companies converted to 3D NAND technology. So in 3D NAND technology, the way is to increase the word line layer. So you can see the 24L, 32L. This L means layer. So the first generation was the 24 layer, but and then 32, 48, 64, 92, and this year 128 layers product is already presented. So in this document, you can also see that the chip capacity is doubled in some generation. That means this chip is 128 gigabit, and some chips in after later generation it has 256 gigabit, and some has 512, and some has 1 terabit. So why it is doubled? Why it is doubled, do you think? For customers, to make the customers use large capacity of SSD and large capacity mobile phone? No, that is not the answer. The answer is cost efficiency. Cost efficiency. You can see this dark brown color. This area is called peripheral circuit. So if you increase the number of word lines, you can make the memory cell array decrease, right? But this peripheral circuit cannot be decreased. So if you do not double the chip capacity and just make the word line more and more, later most of the chip area will be the peri area. So there is a proper chip capacity according to the number of word line layers, and now it is around 512 gigabit. That is the proper capacity. And you can also see the MLC, TLC, and QLC like this. And what does it mean? SLC means single level cell. That is 1 bit per cell can be stored. So 1 bit per cell needs 2 states. And MLC is a multi-level cell, and it has 2 bit per cell, so 4 state. And TLC is triple level cell, and QLC is quadruple level cell. So it is the state-of-the-art one, and it has 16 states just in one cell. This is the cell array structure of 2D NAND and 3D NAND. So in 2D NAND, word line is here, so it runs through the X direction of the chip, and bin line runs across the Y direction. And the NAND string is also same as bin line. It runs through the Y direction. But in 3D NAND, word line is kind of plain. So it is XY. The direction is XY plane, and then word lines are stacked in Z direction. So the channel is here, the green one. You can see that. Can you see that? So channel current flow through the Y direction. And then bin line direction is the same as 2D NAND in Y direction. And you cannot see clearly here, but there's some string select line that can distinguish along the X direction. So we can distinguish all the cells in X, Y, Z direction. And this is the 3D NAND cell structure, just a one cell structure. There's some difference between this left side 2D NAND and right side 3D NAND. So the first is, as I said before, current flow direction is different. In 2D NAND, in this channel, the direction is horizontal, but in 3D NAND, in this in this yellow one, current flows in vertical direction. And in 2D NAND, electrons are stored in polysilicon layer that is called floating gate. In this figure, this blue one. But in 3D NAND, the material is different. This blue color one is charge trap layer, and material is nitride. So used material is different. And and the current path in 2D NAND is silicon substrate, but in 3D NAND, the channel is polysilicon here. The one thing you should notice here is that 2D NAND is not equal to floating gate storage, and 3D NAND is not equal to charge trap storage. Do you understand? That means 2D NAND can be fabricated with charge trap layer, and also 3D NAND can be fabricated with floating gate storage. It's all possible. But most of the mass-produced NAND products have this kind of structure. So this is 3D NAND chip architecture, and here the bottom one is peripheral circuit, and this one is called page buffer, that is sensing circuit. Yeah.
You said that each cell can have multiple states, right? In the slide before this. Yeah. So how are those multiple states stored? I mean, for each cell.
You mean how to make these many states?
Yes.
It relates to the number of electrons in the charge trap layer. So in QLC state, the erase state, the left one, this state doesn't have the lowest number of electrons, and the right one has many electrons here. So the number of electrons can distinguish this state.
Excuse me. Can you say that free on that slide? Yeah. So next one. Next one. Yeah, this one. Can you say that 3D NAND structure can become a gate all around?
Yes, it is always gate all around. Because it's.
I find in the logic area it's hard to make gate all around.
Yes, so logic area, maybe I'll explain with this. So what we can see in that figure is this area. The area, or memory cell array area is gate all around.
Yeah.
But the peripheral circuit here, that is all like just similar to normal logic, or normal logic circuit. That use silicon substrate. Okay.
Do you know why the limitation of logic transistor cannot build gate all around like the memory?
Yeah, many reasons are there, and maybe some stability, and most important thing is if we make this 3D GAA structure, gate all around structure, this have very short gate length, and the on-off ratio is very bad. So it is enough for just for memory cell, but we cannot use this cell to the logic circuit.
What's the difference between floating gate and factory?
The material is different. For the floating gate, polysilicon is used, and polysilicon is for the floating gate, polysilicon is highly doped. So you can think that floating gate is like a conductor, highly doped silicon. But charge trade layer is not doped, and just nitride is used. So nitride is fundamentally that is insulator, right? But that has some traps that can store the electrons. So some characteristic is different. Okay.
So for 3D NAND, what's the dimension of your channel, like the radius?
You mean gate length and?
Yeah, like just the channel diameter itself.
Channel diameter is around 100 nanometer.
Okay, so is everything deposited by ALD, like the gate?
No. It cannot be because of time.
Okay.
Yeah.
Okay.
And the gate length is around 30 to 40 nanometer.
So is the 3D structure monolithic or die-stacked?
Oh, sorry, die-stack.
Or monolithic
Monolithic or die-stack?
for the 3D?
Or what I talking in 3D is just in one wafer.
Oh,
so
just one wafer.
Yeah,
Oh, okay.
and die-stack is not used here.
Okay.
But then you said there's like 200 or 64 layers of memory stacked already happening there.
Yeah, how do you do that within one wafer?
I will explain in later pages. So maybe you could see these kinds of figures of a 3D NAND. So, okay, I will explain first about this chip architecture. So it is peripheral circuit, and this is page buffer, the sensing circuit. And this purple color one is the memory cell array. And then this side, the light blue color, this is a row decoder. So this area, the channel holes and word line stairs, that is the part of here, just near the row decoder. And the figure that is that have many channel holes and slit, like a long line-shaped slit. This is the part of center of the memory already. Okay, now I will explain how to make the 3D NAND. This fabrication method is called gate-less, and this is used in Samsung and Toshiba. So first, nitride and oxide is deposited on the substrate, and one by one, like this. So if we make 64 layers, we should deposit 64 times. And then etch the hole for the channel, and then we deposit the polysilicon. We can see this green color. And then we fill the core of this channel hole with the oxide. So the channel, the polysilicon channel looks like macaroni. So it is called macaroni structure. It is not a joke. It's a real structure. And then this long line-shaped slit is etched. And then we use red etch process to remove the nitride, pink color nitride. We remove the whole nitride here. And then tunnel oxide is deposited. And then next is nitride train. It is later it is used as the charge storage. And then high-K dielectric is deposited. And the blue color, the metal, is deposited. It is filled with space. And finally, the metal is separated by etch process. So this blue color metal can act as a word line. And this is the gate first structure. That is, maybe you can see that Intel and Micron. The first fabrication process is oxide and waterline polysilicon deposition one by one. And then polysilicon is recessed like this here. And then IPD, that is blocking layer, blocking oxide, is deposited. And then floating gate, the polysilicon is deposited. And the polysilicon floating gate is separated by the isolation etch. And then finally, the tunnel oxide and channel is formed like this. So, the first formed waterline gate is not replaced. So it is called gate first process. But Intel and Micron they cooperated, but until since last year they stopped cooperation. So maybe the Intel is the only company that used this gate first process.